All right, y'all. So tonight we're going to be going over Exam 2, Spring 2022, Question 1. And this type of problem can come up on the exam. I'm not saying it's going to be for certain, but it definitely can. This is very similar to the first exam, where we found the electric field at an observer point due to an due to a surface charge, volumetric charge, or some charge density. In this case, we're trying to find the potential at an observer point instead of the E field. And for this specific problem, make sure you read the problem and make sure it's very clear that it tells you the potential is 0 at infinity or 0 at some point, because you're going to use that as your reference point. Okay? Very important that you use this, because the equation that we're about to use can only be used when this is in effect. The equation being the potential at some r is going to be equal to the surface integral of rho s of, again, that r ds prime divided by 4 pi epsilon naught r. And again, if you want to make sure and go look at the notes to figure out when you can't use this, basically whenever potential is not 0 at infinity, you should look at the notes. It's towards the very bottom of one of the notes. I forget exactly which one, but just make sure to go over it. But all the ones I've seen in the past exams, they use potential at 0 is infinity, so you shouldn't have to worry too much about it. Just be wary of it. Anyways, now that we have this, we know rho s. Rho s is 1 over rho cosine squared phi. And now what we have to do is we have to figure out, well, what is ds prime? Well, ds prime, we are given an annulus, or a washer, of surface charge density from A to B. That's all we're given. Well, with ds prime, what do we know? This is a horizontal section, or cross-sectional area of a cylinder. From note 6 coordinate systems, we then know is ds prime is going to be equal to rho prime, d rho prime, d phi prime. Why am I putting these primes? Well, these primes, they are your depiction of the charge, where the charge is. Very, very important that you put these primes. If you don't put them, he's going to take points off. He's already told us. Just be very careful about it. Now, what else is r? R is unknown. R is going to be the distance from a point on our surface charge density to the observer point z. So, when I say a point on the surface charge density, I literally mean any point. It can be this point, this point, this point, this point. It could be anywhere. So what is a good way to define this point? Well, we're going to be using rho prime for the distance from the origin to any point on the surface charge density. Z prime will, of course, not Z prime, but Z will be the distance from the origin to the observer point, and that will not change unless our observer point changes. But this is going to be Z. Let's say we use, let me erase all these other points. Let's say we use that point. Well, then this point is rho prime, right? Put that a little better. And now this point to this point will be R. So R is going to be equal to the square root of rho prime squared plus Z squared. Remember, this makes a right triangle always. And that's going to be our R. Again, this is from the first exam. This is just a little bit of a refresher, just in case y'all don't remember. But now we can pretty much solve this problem. Remember, this is from 0, 0, z. The potential at our observer point is equal to the double integral, because it's a surface integral, of 1 over rho prime, do not forget the prime, cosine squared phi prime. Just because in the problem they don't give you prime, it is describing a charge density, and so we're going to put primes on them. Now it's going to be times 1 over 4 pi epsilon naught square root, because remember this is r, rho prime squared plus z squared ds prime, which is rho prime d rho prime d phi prime. Now one thing we can get out of the way is this rho primes. Because of the Jacobian, we can cancel those out. And now, what else don't we have? Well, we don't have our bounds of integration. Be very careful about which one you put first and which one you put second. Which bound of integration goes on the inside and which one goes on the outside. Which one should go on the inside? Well, looking at our little d phi prime and our d rho prime, the inside should match the inside integrand. So this bottom one will be rho prime is equal to, well, where does the surface charge density begin? It starts at A. When does it stop? It stops at B. Now d phi prime, let's say we're going to start at phi prime is equal to 0, because remember, this is a circle. So phi is an angle. If it's a full circle, it's from 0 to 2 pi. So now what do? Well, we can now split our integral up. This is going to be equal to 1 over 4 pi epsilon naught times the integral from 0 to 2 pi. You see we're doing d phi prime first. Which function on the inside of the integrand has phi prime? Well, cosine squared does. Nothing else does. Don't forget the d phi prime times the integral from a to b, because now we're doing rho prime, of 1 over the square root of rho prime squared plus z squared d rho prime. Now I'm going to tell you what this is, because this will usually be on a formula sheet, but I honestly don't want to have to do power rule and then chain rule. This is going to end up being pi. So what do we get? We get 1 over 4 pi epsilon naught times pi times the integral of this. And the integral of this is going to be given to you at the top, or you should write it down. It'll be in the table of integrals. This is going to be equal to the natural log of rho prime plus the square root of rho prime squared plus z squared, evaluated from a to b. And now what can we do? Well, we can cancel out these pi's, so we're left with 1 over 4 epsilon naught, don't forget these equal signs here, of natural log, replace rho prime, not z, rho prime with b and a. So b plus square root of b squared plus z squared minus natural log of a plus the square root of a squared plus z squared. Now, we're subtracting natural logs from each other. That it's an equivalent statement, is what? Natural log of the first natural log divided by the second natural log. And if you want to play around with the calculator and figure why this happens, you can. All the power to you. I'm not doing that. But this is our answer. This is the potential at Z, and do not forget your units. Volts. This is our answer to part A. Now, part B. Oh, but hopefully y'all understood this part A. Really, it's just setting up the integral. Because we're given a surface charge density, it's a very simple equation. Remember, this must be true for you to use this. All right. Now, part B asks us to evaluate sort of a potential, the same point. Oh, now the change is the potential is now 0 at the origin. So what have we done? What have we done? We've added, we now know the potential at the origin is 0. This point, this is 0. Well, we're adding now a boundary or an initial condition. So now we know, we'll call this part B, we know the flux, oh my god, the potential at 0, the origin, we'll call this the origin, we'll put a little line through it, is equal to 0. Well, this is also equal to 1 over 4 epsilon naught natural log of b plus the square root of b squared plus z squared over a plus the square root of a squared plus z squared plus c. Now, why did I go about rewriting this guy? Why should that even be here? Well, remember, why did we do this integral? What was this integral for? This integral was to find the potential at any value r, or I guess in our case z. If our observer went up, if he went up to, if z initially was 1 meter, and then it went up to 10 meters, this equation will hold. If z goes to negative 5 meters, this equation will hold. Okay? So z can be arbitrary. But now, we're given an equation, or we're given a point at which z is equal to 0, and we know that potential is 0. So we need to find this initial value c, because we're now integrating. So what do we do? Well, we know, again, z is 0, so let's make this 0. Let's make both of them 0. Now, what happens to the inside of this? Natural log of b plus the square root of b squared. Well, that's just b plus b, which is 2b. And the denominator is the same way, it's 2a. So this is equal to the natural log of b over a. So that means 0 is equal to 1 over 4 epsilon naught natural log of b over a plus c. And now c is equal to negative 1 over 4 epsilon naught natural log of b over a. That is our initial condition. So now, this is how the potential will change at value z. We will, again, take our initial, or not initial, but our original equation where z can change, and we have to add on our c value, which is minus 1 over 4 epsilon naught natural log of b over a. Do not forget your units. So this is the answer to part B. Know for certain how to do this initial condition type of question. If we get a question like this, where we have to find the potential at some observer, we will most definitely be asked to find, to use the initial condition type of formulas or concept. Be very careful, because this 0 can change. It can change to some voltage. What if at 0 it's 10 volts? Well, it's the same thing. We get 10 minus this. So just be careful with what they give you. Be careful about what they're saying. And of course, do not forget the proper notation for your integration. It will take off points for you. Anyways, hopefully this cleared up some confusion or helped you out with being able to solve it. If you have any questions, please let me know. Also, I wanted to let you know in the previous video actually, you cannot do that current V is equal to IR. You can't do V is equal to, actually I can just pull it up right here, right? This guy. Oh, look, I already erased it. Okay, you cannot do the V is equal to I naught times 1 times 10 to the minus 6, because the current is not the same. What this question is saying is there's a current, there's a magnetic field induced, or I guess, hold on. Yeah, there's a magnetic field induced by the current somewhere else in the room. That is not the same current that's flowing in here, in this loop. So be careful about what they're giving you. That's my bad. I'll make sure to put a note on the first video. But be careful, you cannot do this. You found out what these voltages were. So you have to use VDR. Just be careful. That's my bad. Sorry about that. Yeah, see, I put current in here. Obviously, that's not the same current that's going through the wire. So we can't do that. But this still holds, honestly. So we're good. All right. Hopefully this one made sense, though. If you have any questions, please let me know. But thanks for watching.